Many finance teams in US companies initially approve an AI initiative because the numbers appear clean and controllable on paper. Moving labor costs into usage-based compute suggests expenses will rise in quiet proportion to actual demand. The promise of flexible operating spend feels structurally sound in budget discussions, where a cost that activates only when the system runs appears easier to justify than one embedded permanently in salaries or fixed infrastructure. That distinction often reads as disciplined capital allocation. Then the system moves into production. A customer support tool that handled steady daily traffic encounters a product launch, a marketing campaign, or an earnings-related surge in inquiries. Within a single reporting period, the monthly inference bill rises sharply, often without any corresponding change in headcount or strategic direction. The business itself appears largely unchanged, yet the cost profile begins to move in ways the original model did not anticipate. What initially presented as a controlled shift in cost structure starts to behave less predictably. The working assumption is straightforward. Replacing fixed salaries with pay-per-use infrastructure should produce a stable, responsive expense layer. In practice, the behavior diverges. Unlike conventional software licensing or basic cloud services, the cost of each interaction does not scale in a smooth, linear fashion. It responds to changes in volume, but also to how that volume is expressed, through variation in inputs, differences in context length, and the gradual expansion of workflows as systems evolve. Variable cost, in this case, behaves predictably only under conditions that rarely persist. In accounting terms, the cost remains variable, yet in operational terms it does not behave that way. As systems move beyond narrow use cases, cost behavior begins to reflect the structure of the work being performed rather than just the amount of activity. A modest increase in usage, combined with richer interactions or expanded context, can produce a disproportionate rise in cost without any visible shift in business activity. The surface signal remains stable, while the underlying resource demand shifts. This pattern emerges from the structure of inference itself. Each request draws on compute, memory, and energy in proportions that shift with context length, reasoning depth, and the presence of chained operations. A simple query may remain inexpensive. A more involved interaction, drawing on prior history or conditional logic, can increase resource consumption several times over, often without clear visibility at the business level. External conditions reinforce this effect. Compute availability changes, GPU capacity tightens, energy pricing shifts across regions, shared infrastructure becomes constrained. These factors can move unit costs independently of usage levels, creating periods where expenses rise even as activity appears steady. A useful way to frame this is through two cost trajectories. One rises steadily with volume, the other begins lower, reflecting early efficiency, but bends upward under pressure before stabilizing again. The divergence between these paths becomes most visible during periods when cost predictability matters most for quarterly planning and budget reviews. This non-linear response defines the operating boundary many enterprises encounter once pilots transition into sustained use. Rather than disappearing with maturity, this behavior becomes easier to observe. Improvements in monitoring and optimization clarify where variability originates, but they do not remove it. What changes over time is not the presence of volatility, but the organization's visibility into its drivers. As usage expands across departments, interactions become more layered, Workflows extend across multiple steps. Systems that began with narrow functions gradually take on broader operational roles. These changes rarely register as formal scope expansion, yet each one subtly shifts how resources are consumed and where costs accumulate. In hybrid environments, this dynamic becomes more pronounced. AI workloads operate alongside legacy systems that were never designed for highly elastic demand patterns. Network limits, storage boundaries, and shared capacity constraints cause the new cost layer to reflect frictions from the wider infrastructure. What appears variable at the application level begins to inherit structural constraints from the underlying system, making isolation more difficult in practice. In day-to-day operations, these effects appear as uneven usage patterns rather than clean growth curves. Adoption expands in bursts, often driven by internal experimentation or external triggers. Because each interaction is directly measured through token-based billing, small increases in sophistication or context can produce outsized cost movement with limited advance indication. To maintain low baseline costs, many teams rely on flexible infrastructure options such as on-demand or spot resources. Under stable conditions, this approach works well. Under constraint, pricing adjusts quickly, or capacity must be secured through more fixed commitments. The result is a cost structure that shifts between flexibility and constraint, depending on system conditions. This creates tension within standard quarterly budget frameworks. Late-period cost movement can be difficult to offset without affecting other initiatives. Over time, the expense layer becomes more integrated into routine operations, reducing the organization's ability to adjust it quickly without secondary effects on performance or service continuity. A clearer perspective emerges when inference is treated as its own distinct operating rhythm, separate from training costs and general infrastructure spend. This shifts attention toward workload composition, token usage, interaction depth, retry frequency, and process structure, rather than relying solely on aggregate cost totals. Some organizations introduce tighter boundaries on prompt complexity or workflow design to limit unnecessary escalation. Others build modest capacity buffers or adjust service expectations around peak periods. These measures improve visibility and control, yet they do not fully remove the underlying uncertainty. The distributed nature of compute infrastructure, combined with continuous advances in model architectures and shifting supply-side dynamics, maintains a structural layer of unpredictability that cannot be engineered away entirely. The genuine economic advantage emerges not from the pursuit of perfect stability, but from the disciplined acceptance of this behavior as an inherent feature of operating AI systems at meaningful scale. Organizations that evaluate performance according to the stability of their operating cost under changing conditions, rather than assuming consistent linear scalability, develop a more grounded understanding of where the model continues to deliver value and where embedded fragility persists. Looking again at the two cost trajectories, the nonlinear shape does not disappear with scale. It adjusts, but the fundamental responsiveness to demand, workload complexity, and resource constraints remains embedded. Understanding these persistent frictions matters as much as grasping the potential efficiencies. In the end, the underlying physics of variable cost volatility shapes real outcomes more decisively than the technology itself.